Welcome to my channel and thanks for stopping by. Have you been looking for how to reduce the dimension of your data so that there are only important components in the data and you don't know how to do it? Or have you heard of principal component analysis or PCA and you don't know how to perform the analysis? If that has been your case, then this video is for you. Because in this video, I will be demonstrating how to perform principal component analysis in XPSS. My name is Titocan and this is Titocan Solutions, a YouTube channel for improving the knowledge of how to do things. But before I go into the demonstrations, let me quickly give you the synopsis. Principal component analysis, otherwise referred to as PCA, is a statistical technique that is used to reduce the dimension of variables in a dataset. It is an important analysis that should be performed by everyone who has dataset with a large number of variables. It is mostly used to reduce the dimensions of continuous or scale variables and ordinal variables respectively. But in XPSS, principal component analysis is carried out as a statistical method in factor analysis procedure. So in most cases, especially in using XPSS, principal component analysis and factor analysis are interchangeably used to mean the same thing. Now let me explain the principal component analysis by a simple rule of thumb. In every dataset, each variable is a component. But when all the variables are subjected to performance in an analysis, some of the variables perform more than the others. Those variables that have a higher amount of performances or that contribute a higher percentage to the output are referred to as principal components. And the principal components are usually a function of the eigenvalues. So when you factor out the principal components among the many variables in your dataset and delete the remaining insignificant variables, what you have done is that you have reduced the dataset from its originally large number of variables to a small size number of variables that still preserves as much information as possible. As a rule of thumb, smaller datasets are easier to explore and visualize. To perform principal component analysis, several mathematical steps are involved. But in XPSS, all the mathematical functions have been activated behind the scene to perform the required given commands. So your job now is to follow my lead as I demonstrate how to perform principal component analysis in XPSS. This is the dataset I will be using for this demonstration. As you can see, this dataset is fictitiously generated to suit the demonstration and it consists of 20 variables ranging from x1 to x20. My objective in this video is to reduce the dimension of this dataset to a fewer number of principal components, and the only way to do that is to subject this dataset to principal component analysis. But before doing that, there are a few assumptions that your dataset must satisfy in order for it to be tenable for the analysis. The assumptions are: 1. Your data must have multiple variables that should be measured at the scale level or be ordinal variables measured as Likert scales. 2. There should be a linear relationship between all variables. The basic reason for this assumption is that a principal component analysis is based on Pearson's correlation coefficients, and as such, there needs to be a relationship between the variables. You can test for this assumption using a matrix scatter plot. 3. Your data should have sampling adequacy. This means that the data you are submitting for principal component analysis should have large enough variables or sample size. Effectively, you should use Kesa-Meyer-Hawkins, simply referred to as KMO, to measure the sampling adequacy for your data as you perform the PCA analysis. 4. Your dataset should be suitable for data reduction. Basically, there should be adequate correlation between the variables in order for the variables to be reduced to a smaller number of components. Effectively, you should use Bartlett's test of sphericity to check for this assumption as you perform the PCA analysis. And 5. There should be no significant outliers in your dataset so that there is no disproportionate influence on your results. You can use box plot to check for this assumption. But please, note that your dataset must satisfy these 5 assumptions, otherwise, the results of the PCA you will get might not be valid. Based on these guidelines, I am glad to inform you that this dataset I am using for this demonstration has satisfied all 5 assumptions and so is tenable for this analysis. But if you want me to produce a video tutorial on how to test for PCA assumptions, please kindly let me know in the comment section of this video. Now, to perform principal component analysis, go to the menu bar and click on Analyze. From the sub-menu, put your cursor on Dimension Reduction. And from the drop-down options, click on Factor. And this opens the Factor Analysis dialog box, as you can see. Now, from the box on the left, click on the first variable, sample 1. Then hold down the Shift key on your keyboard, scroll down, and click on the last variable, sample 20, to select all the 20 variables. Then, click the transfer arrow key to move them to the variable box on the right. Now, let's begin to give the SPSS system commands of what we want it to do for us. Click on the button for descriptives to open the Factor Analysis Descriptives dialog box. In this dialog box, the box for Initial Solution under Statistics is already checked by default. If your own is not checked by default, please kindly check the box now, because we need this command to give us the initial solutions for commonalities and total variance explained. Then, check the box for univariate descriptives. This command will produce the descriptive statistics of the variables or components. This may not be necessary for you to do, but I wanted it because I want to indicate the total number of cases in my dataset for this demonstration. In the correlation matrix section, check the box for coefficients. This will produce the correlation matrix results table. And then, check the box for KMO and Bartlett's test of sphericity. These two tests are fundamental in this analysis because we need them to test for assumption number 3 and 4. KMO stands for Kesa-Meyer-Hawkins, and it is used to determine whether the data you submitted for principal component analysis is adequate and suitable for the analysis, or whether the dataset has enough variance that can be partitioned using principal component method. While the Bartlett's test of sphericity is used to test the null hypothesis that the variables in the population correlation matrix are uncorrelated. That is, Bartlett's test of sphericity tests whether the correlation matrix is significantly different from an identity matrix, in which case correlation between variables are all 0. Other options can be omitted for now. Then click Continue to close this dialog box. Now, click the button for Extraction to open the Factor Analysis Extraction dialog box. As you can see, the default method for extraction is principal components. There are other methods of extraction, but since we are doing principal component analysis, I will leave the default selection unchanged. For the Analyze section, leave the default selection for correlation matrix unchanged, because for correlation, the data is standardized and the principal component analysis actually has to do with the correlation between variables. For the Display section, check the box for Script Plot. The script plot will produce the visual summary of the total variance explained by each component based on the eigenvalues, and helps to determine the number of factors or principal components to retain. Eigenvalues greater than 1 are always the criterion used to extract the principal components. So for the Extract section, I will accept the default selection to extract the factors based on eigenvalue greater than 1. However, you can also choose to force the SPSS to produce a fixed number of factors as you preconceived. But for this tutorial, I will extract the factors based on eigenvalue greater than 1. Now, for maximal iteration, if the cases of your variables are less than 300, you might want to increase the maximal iteration for convergence from 25 to 50, or 75, or even 100. Because if the sample size of your data is small, the convergence becomes increasingly more difficult. But if you have a sample size that is 300 or more, you can leave the default maximal iteration index unchanged. This is a significant factor you must put into consideration when you perform principal component analysis. But in my case, I will leave the default value of 25 unchanged since my variables have more than 300 cases. Now, click Continue to close this dialog box. click on the button for rotation to open the factor analysis rotation dialog box. There are two basic methods of rotation. They are the orthogonal rotation method and the oblique rotation method. The goal of factor rotation is to improve interpretability of the factor solution by reaching a simple structure. However, in SPSS, three options are provided for orthogonal rotation, which includes varimass, quatermass, and equalmass. This orthogonal rotation assumes that factors are independent or uncorrelated with each other, while the oblique rotation method includes direct obliquing and promass. This oblique rotation assumes that factors are dependent and are correlated with each other. However, the most commonly used rotation method by researchers is varimass. So for this tutorial, I will check the radio button for varimass as it suits the data for this demonstration. In the display section, check the box for loading plots. This selection will produce a 3D plot in space depending on the type of rotation you choose. It is just for visual purposes only. But for this tutorial, I will leave the box unchecked. Then click Continue to close this dialog box. Now, to save the factor scores to your dataset, click the button for scores, and in the dialog box that opens, check the box for Save as Variables and leave the default method as regression. Click Continue to close this dialog box. Finally, click the button for Options to open the Factor Analysis Options dialog box. This Options dialog box gives you the exclusive right to decide how to fix any missing data or missing value in your dataset, and the exclusive right to decide the format of how to display the coefficients in the component matrix table. Now, if there are missing data or missing values in your dataset, then select the appropriate method of your choice to handle the missing data from the list of options in the missing value section. But since my data don't have any missing value, I will leave the default choice unchanged. For the coefficient display format, check the box for Sorted by Size to sort the coefficients according to sizes, and check the box for Suppress Small Coefficient to suppress the coefficient less than the absolute value of 0.1. But for this tutorial, I wish to increase the absolute value below which any coefficient can be suppressed. So I will change the absolute value from the default choice of below 0.1 to 0.3. You can actually choose within the range of 0.1 and 0.5, but any value less than 0.1 or greater than 0.5 is not allowed. This suppressed threshold helps to sanitize the result table of the rotated component matrix from displaying many irrelevant coefficients. Now, at this point, we have successfully configured the SPSS system to perform principal component analysis. So click OK to produce the results in the output window. As you can see in this output window, the results have been produced in many different tables. Only few of the results tables are important to talk about. So among these results tables, I will restrict my discussions of the results in the following order. 1. The descriptive statistics table. 2. The KMO and Bartlett test table. 3. The correlation matrix table. 4. The commonalities table. 5. The total variance explained table. 6. The script plot. And 7. The rotated component matrix table. Now, let's scroll up to descriptive statistics table. As you can see in this table, the descriptive statistics shows the mean, the standard deviation, and the number of cases per component. As you can see, there are 500 cases per component or variables, and there is no missing data. So using 25 as the maximum iteration for convergence was good, because the length of my data is more than 300. Now, let's scroll down to KMO and Bartlett's test table. This table of results provides an answer to the test of assumption number 3 and 4, which has to do with sample adequacy and suitability. If the value of KMO is greater than 0.7, it means that the dataset is adequate for the analysis and there is enough variance in the dataset that can be partitioned using principal component analysis. This also means that the data is scalable. But your data will be inadequate for principal component analysis if KMO is less than 0.5. So as you can see from this table, the KMO is 0.840, which is greater than 0.07. This indicates that the dataset is adequate and suitable for principal component analysis because there are sufficient items for each factor. For Bartlett's test of sphericity, if the p-value is less than 0.05, it means the variables in the population correlation matrix are uncorrelated and are significantly different from identity matrix. So as you can see, the p-value of the Bartlett's test of sphericity is 0.000, and this is less than 0.05, indicating that there is enough variance in the dataset because the correlation matrix is significantly different from an identity matrix. In case you don't know, an identity matrix is one where there is no correlation between variables. As you can see also, our dataset is adequate and suitable for principal component analysis or for factor analysis. So we can now go ahead to interpret the other results table. Let's take a look at the correlation matrix. There are so many coefficients here, and it won't be possible to talk about them individually. So I will discuss this table on a general note. This table of correlation matrix shows how each sample is associated with each of the other sample. Some of the correlations are high, while some are low. Coefficient close to 0 can be regarded as low correlation, while coefficient as much as 0.6 or greater can be regarded as high correlation. As you can see from this table, coefficient as high as 0.6 or greater indicate that two samples are strongly associated and probably can be grouped as a factor. As regards samples with low correlations will not have high loadings on the same factors samples with high loadings are grouped. The next table of result is commonalities. The commonalities table provides information showing extent to which a variable is explained by the components before rotation, which is the initial solution as you can see in column 2, and after the rotation as you can see under the extraction in column 3. In this table, the value for the initial solution is 1 for each variable, which means that each variable is well explained by the components. But after the rotation, the values for each variable under extraction are all less than 1. So the closer to 1 the variable is, the more the variable is well explained by the components. Here, every sample appears to be well explained by the component except sample 17, which has 0.496 as a low commonality. Now, this leads us to the next table, which is the total variance explained. This table shows how the variance explained is divided among the 20 factors. This table is divided into 3 basic groups, such as the initial eigenvalues, extraction sums of square loadings, and rotation sums of square loadings. But among these listed information, the 3 columns of the rotation sums of square loadings, which are the 3 rightmost columns of this table, contains the most important information. In this table, the columns for total is the eigenvalue, which is the measure of explained variance, and as you can see, the loadings decrease down the column. Since we indicated during the procedure to extract the factors based on eigenvalue greater than 1, the principal component analysis has extracted 4 factors or components that have eigenvalue greater than 1. As you can see, component 1, component 2, component 3, and component 4 have eigenvalues greater than 1, while component 5 to 20 have eigenvalues less than 1. So the components with eigenvalues greater than 1 are extracted from the 20 variables as the principal components and deposited in the second group under extraction sums of square loadings of this table. As you can see, the total, the percentage of variance, and the cumulative percent are all the same as the initial eigenvalues group. This means 4 factors have been retained by extraction, while the remaining 16 variables have been omitted because they didn't meet the criterion of useful eigenvalues. Hence, there is no information below the 4th principal component. Now, to be able to correctly interpret the results of this table, you should consider the 3rd group, which is the rotated sums of square loading sections of this table. At this part of the table, the total, which is the eigenvalue, the percentage of variance, and the cumulative percent are all different from the previous subgroups of this table. This is due to the orthogonal rotation by virtue of the choice of variables which we made under rotation during the PCA procedure. As you can see, the eigenvalue of the first component is 5.926, and this component explained a variance of 29.632%. The second component has eigenvalue of 4.472 and explained a variance of 22.361%. The eigenvalue of the third component is 3.609, possessing a variance of 18.045%. And the fourth component has eigenvalue of 2.425 with an explained variance of 12.123%. The cumulative percent column shows the value when you add up all the percentage of variance. So as you can see, the total variance explained by the four extracted components or factors is 82.161%. This means that 4 components among the 20 variables in our dataset account for 82.161% variance in the dataset. And this also means that the remaining 16 variables put together could only account for negligible amount of variance, which is about 17.839%. So the PCA analysis strongly suggests that the 20 variables of the dataset can be reduced to just 4 factors or components. Now, let's scroll down to the script plot to see the visual expression of the loadings of the eigenvalues against the component number. As you can see, 4 components from the left are greater than 1, while the remaining 16 components are all less than 1. So, the script plot plays an important role in visually representing the number of components with a sufficient amount of variance that can represent the entire dataset. At this point, there is a question we must ask and provide answers to. The question is, what are the original variables associated with the principal component of factors that have been extracted? To answer this question, scroll down to the rotated component matrix table. The information provided by this table is also referred to as the loadings and is the key output of principal component analysis. It contains estimates of the correlation between each of the variables and the estimated components. In this table, the loadings can either be positive or negative. Typically, when interpreting component matrix results, correlation of less than 0.3 or 0.4 are regarded as trivial or mere loadings. However, the correlation of minus 0.4 or minus 0.3 and 0.0 between variables and components are regarded as trivially small. Correlation between 0.7 and 0.9 can be regarded as strongly correlated, while between 0.5 and 0.6 can be regarded as moderately correlated. So for this tutorial, I will consider only the strongly correlated loadings. Accordingly, sample 2, sample 1, sample 4, sample 9, sample 5, and sample 6 are strongly correlated with component 1. However, sample 6 strongly correlated with component 1 and moderately correlated with component 3. Based on the choice of variables which provided orthogonal rotation, each component is supposed to be uncorrelated, so there might be a need to remove sample 6 from the partition. Similarly, sample 16, sample 19, sample 20, sample 13, and sample 18 are strongly correlated with component 2. Sample 14, sample 25, and sample 7 are strongly correlated with component 3. And finally, sample 8 and sample 12 are strongly correlated with component 4. As you can see, the 4 principal components truly represent majority of the variables in the dataset. So the 4 factors are good representation and they can be used for further analysis instead of the 20 variables in the original dataset. These factors have been added to the dataset, and if you return to the data view window, you will see the new variables. This is factor 1, factor 2, factor 3, and factor 4, and they are all also called principal component respectively. This is how to perform principal component analysis in XPSS, and I hope you'll be able to replicate the procedure to reduce the dimension of your own data. But right now, we have come to the end of this video. If you like this video and you want to see more video contents like this, please give this video a thumbs up, share this video, and subscribe to my YouTube channel to receive notification every time I publish new and useful content. Subscription is free. Thanks for your time and subscription, and I hope to see you again in my next video. Bye.